fellow at Imperial on a 4-year-long fellowship. Before being at Imperial, he's been working on research at University of Manchester. He did a 2-year-long fellowship at CERN, and he also did research with Cambridge, where he also did his PhD on the Z boson. Funnily enough, if those of you who were here for the talk yesterday by Professor John Butterworth, Professor Butterworth actually was one of the examiners on Dr. Barter's PhD, funnily enough. And above all his distinguished career so far, Dr. Barter started off at Cambridge with a natural science degree where he graduated top of his class. And today he will be talking to all of you on his research. So thank you very much for being here, Dr. Barter.
It's a pleasure. Can you hear me and see my slides?
Yeah.
Cool. And thanks for talking through some ancient history there. Hopefully I can interest you with some of my current research. So I'm going to be talking about what we know as quark flavor physics. So I thought I'd start by just setting out what I want to talk through to you today. But actually I should start by saying I think this is fantastic. It's a great environment, and I'm sorry it has to be online and done in this format, but hopefully in the near future things will return closer to normal. But what I want to talk about today, I'll start by kind of introducing what particle physics is, what the standard model is, and then I'll start to try and address the questions of what lies beyond the standard model and what are some of the open questions. And I imagine that you've heard similar ideas from previous speakers, but of course there is a certain subjective nature to trying to set out these questions. I'll talk a bit about why investigations of what we call flavour, which I'll define, provide a route to address some of these open mysteries. I'll talk about some of the studies we're making, both how we're making them and what they're telling us, and then I'll close by discussing kind of what's next, what's in the future. So particle physics is really the quest to understand the universe or nature on a fundamental level. And this means investigating the interactions of fundamental particles. So we have this knowledge that there are certain particles that we consider to be fundamental. There may, of course, not be. There may be physics at higher energies that means that in fact these are just composite phenomena. But we have this idea that if we can probe their interactions, we can start to learn about how the universe operates and what the physics of the universe is. And we seek a powerful, simple explanation for how the universe behaves. And the standard model really is just this. The standard model is made up of a bunch of particles, which I'm showing on the left-hand side. You've got your different particles. You've got your matter particles, which are your quarks and leptons. You've got your forces, which are these different boson particles here. And underlying it all, you've got the Higgs field, which gives mass to particles, and the Higgs boson, which is a consequence of the existence of that field. And the standard model takes as an input the idea that these particles exist. It doesn't say why these particles exist. It doesn't say why there are this many particles and so on, but it says, given I have these particles, can I make some predictions for how they're going to behave? Can I understand the physics really of what's going on? And that's captured by this equation on the right-hand side, which you can fit on the side of a mug. Now, this is a Lagrangian for those of you who have come across it. For those of you that haven't come across Lagrangians, it's essentially a formulation of the dynamics of these different particles. It's saying this captures how these particles propagate, but it also captures how they interact with each other. And from this, you can get predictions. Now, this equation on the mark is vastly simplified. Within each term hides a whole bunch of other terms. But the fact that you can fit it all on one mug is quite impressive. And even if you were to write it out fully, expanding every term, you'd only cover a couple of sheets of A4. And that's a stunning achievement for humanity. The idea that we can explain what we think of as the fundamental particles in the universe and how they interact with each other to stunning levels of precision, And it's that simple, it's remarkable. Now, from this, you can build up different other particles. So we talk about the particle zoo. You can build up hadrons, which are made from quarks and antiquarks. They're particles that feel the strong force. Mesons, well, they're a quark-antiquark pair. And examples include the pion, which is an up quark and a down antiquark, and the kaon, which includes an up quark and a strange antiquark. If you wanted to talk about baryons, there you're talking about particles made of 3 quarks, or antibaryons are made of 3 antiquarks. And examples there include the proton and the neutron. And there are also beauty and charm hadrons that contain beauty and charm quarks and so on. And the key point here is that while we have these fundamental particles, which I have on the previous slide, we can build up the other known particles from here. And really this is building up into the idea of what composite particles are. But of course, once you've got the proton, you can combine it with neutrons and form atomic nuclei. You can combine it with electrons and form atoms and so on. And so this really is getting down to the fundamental physics that underlies everything. So the Standard Model is a collection of known fundamental particles and the rules that govern their interactions. It's inherently a quantum description of the universe. It's a quantum theory. And it is the best tested and most successful theory we have of fundamental physics at the highest energies and at shortest length scales. And it is accurate within its own domain of what it seeks to describe. Now, what do I mean by that? Within the questions that you can ask, the Standard Model is able to answer. Every time we've tested it, it has come up pretty much correct. And where it's fallen short, you can make simple extensions to address where it falls short. But it's incredibly accurate. And if you wanted to pick one message from the first 10 years of research at the LHC, it would be the stunning success of the Standard Model, that it has, despite having had so many tests thrown at it, it has passed all of those tests with flying colours. But I think it's fair to say that it is also unable to answer or address questions outside of its own domain. So we consider this. Here are some open questions which the Standard Model doesn't really answer. Why is gravity so weak compared to the other forces? Gravity isn't, in fact, even within the Standard Model, and it doesn't need to be to explain the interactions we see, for example, at the LHC, because gravity is so weak, we don't notice gravity in the collisions at the LHC. It doesn't have a particle that we can think of much more matter than antimatter. It doesn't explain why the strong force behaves in the same way for matter and antimatter. It doesn't answer why there are 3 generations of particles. So I can think of a generation as being, for example, the up quark, the down quark, the electron and the electron neutrino, and then the second generation being the charm and the strange and the muon neutrino and so on. But it doesn't explain why there are that number of particles. It doesn't explain why there are differences between quarks and leptons. We know that quarks feel the strong force and leptons don't, but why are there these specific particles? It doesn't answer why the free parameters in the Standard Model take on the values that they do. The Standard Model has a collection of free parameters, around 20, depending on how you count them. And it doesn't explain why those values are what they are. And it doesn't explain why you have a collection of different particles with such different masses. And it doesn't address what the masses are of the neutrinos, or indeed the mechanism via which neutrinos acquire mass. And so these questions are not addressed by the Standard Model. And therefore, just from the existence of these open questions, we know already that there has to be physics beyond the Standard Model, which means there are new particles and new interactions out there and new explanations. And if we want to answer them, we have to search for new physics that is not described in the Standard Model. And that is what essentially underlies so much of ongoing particle physics research, this quest for a deeper understanding that goes beyond that lies within the Standard Model. Now, there are different ways we can do this. We can do what are known as direct and indirect searches for these phenomena of new physics. So let's take the left-hand side first, direct detection. We can search for particles that are produced directly in collisions. And so when we're making this kind of measurement, we're saying, do I have evidence of new particles being produced at the Large Hadron Collider? And because of Einstein tells us that energy and mass are the same same thing. We can only produce particles up to the energy of my proton collisions. And therefore, in these direct detection where I am directly producing these new particles, I am probing particles at around energy scales of about 1 TeV, because that's the energy essentially of the majority of LHC collisions. The proton-proton collisions are at around 13 TeV. I've also got this idea of indirect detection. So here I can search for the indirect effects and phenomena associated with new particles. Now, these particles are not produced directly in this approach. Instead, we're observing their effects in the same way that if I have nuclear decay, if I have beta decay, that is influenced by the weak force. But we're never actually producing a W boson, the messenger boson associated with the weak force. We're just feeling its effects. We're seeing its effects. These particles are produced way away from these particles are involved in physics way away from their energy scales. And indeed, therefore, by just looking at these indirect detection style measurements, you can probe energy scales up to around 100 TeV by making measurements at much, much lower energies. So what do I mean by this? On the left-hand side, then, I've got a plot taken from the Atlas collaboration, where they've essentially just said, let's look at this particular variable. If I had a new particle produced, I would see this blue line in my distribution. So I would go away and I would make measurements and I would plot on this graph event counts for how often I saw different events as a function of this variable on the x-axis. And if there was a new W prime type particle, it would just follow this distribution and I would see more events out in this region than I would predict from the standard model, because I'd be directly producing it. Whereas the indirect detection method on the right-hand side, what I'm really doing is going away and making high precision measurements of certain quantities, and I'm seeking to interpret whether or not they agree with standard model predictions. And if the agreement is good, then I can say that within this process, there is no evidence for additional phenomena. But if the agreement becomes less good, then maybe I'm starting to feel indirect effects from particles that are not being directly produced, but are still influencing what is going on in the same way that it occurs in beta decay. Now, many of the open questions that I set out can be addressed through the study of quark flavour physics, which is the study of the properties of hadrons that contain beauty, charm, or strange quarks. And here we are explicitly making use of this indirect detection approach. We're going to make a whole bunch of precision measurements of quantities that we know well within the standard model and ask whether they're consistent with each other or whether they agree with those standard model predictions. And if they don't, I'm not saying necessarily that there is a given particle of a given mass that is producing them, but I'm able to say whether or not the standard model is correct. And if it isn't, then I can start to think about what is causing these discrepancies. Now, why am I interested in these heavy flavour particles, for example, beauty and charm hadrons, rather than other parts of the standard model? There are a couple of reasons here. The first is theoretical, that many proposed theories of new physics that go beyond the standard model have interactions that take place preferentially involving the heavier particles rather than the lighter particles. And secondly, within these specific areas, the standard model contribution is relatively easy to disentangle from new physics contributions. So the presence of any new physics would be more obvious, would be easier to see. And indeed, there are dedicated experiments. There's the lhcb experiment at the Large Hadron Collider, where I work, looking at this, but also the Bell 2 experiment. So the Large Hadron Collider collides proton beams, as I'm sure you've heard. Here's a schematic of the ring situated in and around the Geneva area. And we have different experiments that are observing these collisions at different points around the LHC ring. You've got the CMS and Atlas detectors that are general purpose detectors. You've got ELISE that's looking to probe hot dense matter in heavy ion collisions. And you've got LHCb, which is designed to probe flavour physics. And this is a schematic of the LHCb detector. It's about 20 meters long. the proton beams collide here, and then the instrumentation is essentially around one of the two beamlines. Or put differently, if the proton collisions were at the center of the Earth, the angular coverage of LHCb is equivalent to instrumenting very roughly the Arctic Circle. We're covering about 4% of the solid angle. And the reason we can get away with this is if I look at how beauty hadrons are produced at the Large Hadron Collider, if I take my angles of beauty pairs, so this is a B quark and an anti-B quark, the angles θ1 and θ2 with respect to the beamline, I find that the production is strongly peaked with both quarks around the beamline. And because the LHC is symmetric, it's proton-proton collisions, it's around both beamlines, and we choose just to instrument around one. So despite instrumenting around only 4% of the solid angle, we actually pick up around 40% of the B hadrons that are produced at the LHC collisions. And here's an example of what we can see. You've got here just a spectrum of what we measure. So here we're saying I'm going to select pairs of muons that we measure, and the blue distribution is where they're opposite charge. And this is the output, and you can see here that you've got various bumps in the spectrum, and each of these correspond to a different particle measured at different stages within the history of particle physics. Now, the x-axis uses the units of MeV, which are natural units. You may think that's a unit of energy, but you can always convert mass to energy by multiplying the mass by c squared. Or alternatively, you can think of it as being what energy would I need to just produce a particle of this specific mass. Different ways of thinking about what these units are. So what are some of the measurements that LHCb are interested in? Well, we know that the universe exhibits a large baryon asymmetry, which is just a fancy way of saying that there's far more matter than antimatter in the universe. And I can quantify this by saying, if I look at the relative number density of baryons I have, of matter I have to antimatter compared to photons, and I find that if I go away and just evaluate this, I get something of order 10 to the minus 10. Now, the weak force doesn't actually treat matter and antimatter particles identically. So the standard model does allow for this asymmetry, but the standard model prediction of this asymmetry is around 10 to the minus 27. So it can't generate anywhere near the size of the matter-antimatter asymmetry we see in the universe. Or put alternatively, there must be a method to generate this asymmetry that lies beyond the standard model. And therefore, if we go away and compare matter and antimatter processes and look for differences, we might be able to see this new mechanism that might generate this asymmetry. By comparing matter and antimatter processes, we have an excellent laboratory to investigate the effects of new physics. So as I said, these asymmetries in the standard model are introduced via the weak force. And we can think of this in terms of the relative interactions of different quarks to the W boson, which I'm going to quantify with this number VQQ bar. For different quarks. And each VQQ bar is a complex number. And when I'm calculating the rate of antimatter processes in the standard model, I have to take the complex conjugate. And because the complex conjugate of a complex number is different to what you start with, you get differences in your calculations and you introduce differences between matter and antimatter. And if I consider this coupling of the weak force, this VQQ bar is actually a 3x3 unitary matrix known as the CKM matrix. And it's non-diagonal because the propagation states I have within the standard model are not eigenstates of just the weak force. And therefore, I've got off-diagonal elements. And we can access many of the elements of this CKM matrix, which are themselves many of the free parameters in the standard model, by making measurements of heavy flavor hadron decays. This is another reason why it's so good to look at heavy flavor hadrons. And I'm setting out how you'd measure the different numbers here, but note that the ones I've put in light blue, you can get through different heavy flavor hadron processes. In other words, you can measure a large fraction of them at dedicated heavy flavor experiments. Now, I mentioned that this CKM matrix was a unitary matrix. If I think about what that means, I get a bunch of equations which I can set equal to 1, where I'm considering the elements when I multiply it by its unitary conjugate, I get a bunch of elements that are equal to 1 and a bunch of elements that are equal to 0. And the elements that are equal to 0 is essentially saying that I've got some combination of pairs of these elements that sum to 0, but they're complex, and so that maps out a triangle in the Argand plane. And so this is what we know of as one of the unitary triangles. And you can see that it's got a side that I've set equal to 1, and then by dividing through by some elements, I've got 2 other sides and some angles as well. And I can over-constrain these angles and these sides by a bunch of different measurements of heavy flavour physics, many of which are made at the LHCb experiment, and test whether or not they're all consistent with each other. Is this unitary condition of the CKM matrix fulfilled? And indeed, if I look at this, I've got a bunch of different conditions on where this, this specific point in the triangle is, and I find that, broadly speaking, they are all pretty much compatible. I can also look at charm mesons. Matter-antimatter asymmetries in charm meson processes are predicted to be tiny in the standard model, about 0.01 to 0.1%. And I can look and say, do I have differences between the decays of these charm mesons when they're made out of matter combinations or antimatter combinations? And if they are consistent with each other, then I've got something that is broadly consistent with the standard model, where these differences are predicted to be small. But if I've got large differences, then I'm picking up significant effects that might be arising from non-standard model processes. And so I can measure this asymmetry in how often these charm mesons and anti-charm mesons decay to different states. And LHCb has in fact just measured that this asymmetry in these charm meson decays is at the level of about 0.1%. Which is at the very upper end of where you might think the standard model allows, and therefore there are ongoing discussions about the implications of this measurement and how to interpret its consistency with the standard model. Another key aspect of this quark flavour physics are measurements of the relative rates at which B hadron decays. Now, for some processes, for example, where I start with a B quark and I end up with an S quark and 2 leptons, so in this case they might be muons, the standard model prediction is very small. And you can see this by the fact that the Feynman diagram is very complicated. It's got a whole bunch of different vertices that really drive down the rate if I want to evaluate how often this occurs. Now, in this case, because the standard model contribution is so small, new physics contributions might be able to compete and cause significant variation in this rate from the standard model prediction. And so I've got a new physics diagram here that includes a potential new particle called a leptoquark, which might also influence this process. And so we can go away and we can measure one of these processes. And because while we're interested in the quark level predictions, we access the quarks via hadrons, we're going to measure the decays of B mesons to another type of meson known as the K star and 2 muons. And I can get events that are consistent with this decay and measure the angular distribution of these decays and compare them to standard model predictions. So the data points are essentially the angular distribution that I get in my measured events, and the orange are the predictions that I would get if I just evaluate the angular distribution within the standard model. And there's this reasonably significant discrepancy in this region here that might be due to other less well understood parts of the standard model, but might also be arising from standard model, from beyond standard model physics. And this is something we have under ongoing discussions. It's something we're still considering. It's something we're still discussing. We're going away, we're making more measurements. We're trying to understand what the cause of this tension is. Now, the standard model also predicts that different leptons, electrons, muons, taus, behave identically up to various different mass effects. But theories of new physics do not necessarily have this lepton universality, and heavier second and third generation particles, i.e. muons and taus, may be far more sensitive to new physics effects. So we can look at these specific B hadron decays and ask, well, are the decays happening at essentially the same rate, if I just change the type of lepton I'm putting into the decay. They should happen at the same rate. This ratio between the rate at which they occur should be 1 in the standard model. But if I see a deviation from this unity, then I might begin to question whether or not my data are consistent with standard model predictions. And indeed, this specific ratio, considering these K mu mu and KE decays, have been made at a bunch of experiments. You've got previous experiments like Barber and Bell, who have made measurements, and they've found that there is this consistency at the level of 20–30% with standard model predictions. But the LHCb collaboration have recently made this measurement using LHC data, where they've achieved, we've achieved a precision at better than 10%. And here we're again starting to see this potential discrepancy with respect to unity, this potential discrepancy with the standard model prediction. And again, there's nothing concrete here yet, but we're in a place where if this remains with more data, it's very, very hard to explain this within the standard model. And indeed, it's more data that will help us determine if this is a fluctuation or a statistical effect, or whether this is indeed physics arising that lies beyond the standard model. Now, I've presented some places where the data we have are in tension with the standard model. It's important to note that by and large, the vast majority of measurements are in fact consistent with the standard model. But there is at least a picture emerging where there are hints of new physics. And can we include these within a consistent picture? And the answer to that is, broadly speaking, yes. We can explain these hints by adding new particles. And options include a new neutral boson, which we typically call a Z prime, or a leptoquark. And the leptoquark is a specific type of particle that arises in theories that unify how we understand quarks and leptons within a single framework. And it's this kind of theory that sometimes begins to address some of the fundamental questions of why the standard model is structured as it is. Why are leptons and quarks why are they what they are? Why are there different types of fermions? And these particles can have masses as large as 30 TeV over c squared. And that's larger than the collision energy of the Large Hadron Collider. And so they might not be directly detectable, and you do have to rely on these indirect detection methods, though they would potentially be accessible at future colliders. Now, what's happening next? We're upgrading the LHCb experiment. The experiment has undergone a major upgrade over the last 2 years, and we're going to start recording new data in 2022. Now, this is crucial because we're going to increase the proton collision rate at LHCb by a factor of 5, and we're going to be able to triple our data set that we collected over the last 10 years by 2025. And indeed, we are planning for and setting out the case for a further upgrade at the end of this decade. It's important to mention that there are other experiments. The Bell 2 experiment is just starting up. It operates in Japan. This is an E+ E- collider that produces upsilon mesons, which have a mass around 10 GeV, and these are a BB bar pair. And these readily decay to be mesons, which you can then study in detail. Now, this is a very clean experimental environment. They do offer a reduced number of hadrons possible for study. And so it's a very nice complementary experiment to the LHCb experiment. And they should be able to confirm or refute LHCb measurements, for example, of this lepton universality ratio I was talking about, by the middle of this coming decade. And that's really useful because you always want to have any extraordinary claim verified by additional experiments. You don't want to ever rely on one experiment. So just to summarize where we stand there in terms of the field from my perspective, the standard model is extremely successful, but has many open questions. We're able to measure very, very high energy phenomena at much lower energies using precise measurements of quantities that are very well predicted within the standard model. And indeed, this enables indirect searches for new physics phenomena. And it's quark flavor physics that exploits these methods, and it does this through the study of hadrons that contain beauty and charm quarks and how they decay. We have a vast majority of measurements. It's the real story of the LHC, is a vast majority of measurements that are consistent with the standard model, but there are some interesting hints appearing of potential new physics. And this is something that we should be able to really be able to understand further on a timescale of the next 3 to 5 years. It's a really exciting time to be involved. So thanks for listening.
Great, thank you very much, Dr. Barter. Very, very interesting research and very exciting over the next few years what could come out of it. As usual, if you have questions for the Q&A, please put them in the chat. Our first question by Oshi is, what do we hope to discover through the upgrades of lhcb?
Yeah, that's a really good question. Thanks for asking it. So I think one way to think about the upgrades to the LHC experiments is that if you just think about statistics and uncertainties, statistics tend to scale as square root of your yield. And so if I take more data, it takes progressively longer and longer to reduce your uncertainties on your measurements by the same factor, because you're not going as just the amount of data you take, you're going as the square root of the amount of data you take in terms of your precision. And with that in mind, you have to find ways to accumulate data at a faster and faster rate if you want to keep pushing back your levels of understanding. And so in some ways you are addressing the same measurements, making similar measurements to what you've made before, but you are drastically improving the precision you're able to make these measurements at. And if you think about that in terms of the effects of new physics theories, that means if I'm able to drastically improve the precision with which I make a measurement, then I'm sensitive to smaller and smaller effects from those beyond the standard model theories. And therefore, I'm able to make conclusions. I'm able to infer more about new physics. I'm able to probe smaller and smaller new physics effects because of these upgrades.
Great. Another question from Marlene is, how much harder is it to provide evidence for one specific theory than it is to just demonstrate deviations from the standard model?
Yeah,
Do you think to stop narrowing them down soon?
Yeah, that's another fantastic question. You are able to make statements about the particular structure of beyond the standard model theories from the nature of deviations from the standard model. Now, if I just have one number that I measure, which is just a single deviation in a single quantity, that could be described by many different theories. But if I start looking at angular distributions, if I start looking at how I see things arising in different decay rates, then all of a sudden I'm able to pin down the structure of how this new physics behaves, because I've got more information. I'm able to constrain how it behaves more. Now, with an indirect style of approach where I'm saying, well, I see a discrepancy here and I see a discrepancy there, I don't think you'll ever be able to go array and really say, well, it's going to be at exactly this mass that I find this specific new particle. There is always going to be a role for direct detection style measurements, where you go out and you really do just scan through distributions, for example, and look for new particles. But it can guide where you begin to look and so on. And indeed, many of the stories in the history of physics in terms of discovering new particles are particles that are indirectly predicted via these indirect detection measurements where you see discrepancies. And then you go on and you go out and discover what that particle is by looking and really finding it with the direct detection approach.
Another question. Does this mean that there will no longer be any direct detections of new particles at the LHC?
No, absolutely not. It's a really good question. It's a really good point to make. You can always just say, well, maybe this particle has a very, very low chance of interacting with my standard model particles, and you should absolutely continue to do those direct detection searches. It might just be that it's very, very rare for it to be produced, and so you have to essentially go away and continue looking, and maybe you'll find it with more and more data. These two methods are very much complementary, You don't want to use one over the other.
Okay, I think we'll make this one our final question. Have there been any measurements that haven't been declared as discoveries due to the uncertainty of insufficient data?
So that's a fantastic question, and it's something that we have to think about: is to what extent can we claim that a specific deviation amounts to a discovery of non-standard model phenomena? And of course, that comes into experimental accuracy, but it also comes into theoretical accuracy. How well do I understand the prediction that comes out of the standard model? And you really have to understand both sufficiently well in order to claim that your deviation is a deviation. And so it really comes down to the uncertainty. How well do I know my data, and how well do I know my prediction? There's no set limit for the amount of data you need. The larger the effect is, the less data you need to be able to see it. Of course, it's always important to check that effects are consistent, that they behave in a way that is somehow plausible within your data set, that other experiments that can see these phenomena do see these phenomena. And so you want to make sure that you've got different experiments that are able to cross-check each other, and so that if there is an extraordinary claim, an extraordinary discovery, it really is confirmed by different groups working at different experiments. That's really the key thing for a discovery.
I think we have time for one more question then. Do you believe supersymmetry of particles will end up being true? As far as LHC has found, hundreds of predicted particles haven't been detected. What do you think the future holds in this regard?
Yeah, that's a really good question. So there are always theories that make different sets of predictions, and the goal of an experimental physicist is to go away and interrogate whether or not the prevailing theory, the standard model, is accurate, or whether there are evidence for new theories. And you can also go out and make these direct searches. Now, I don't have a belief whether or not supersymmetry will end up being found to be true, because I prefer to be agnostic and let the data guide what I think. It is certainly a plausible theory that merits investigation. And if you speak to some supermetric theorists, they will tell you that it's completely fine that it hasn't been discovered yet for various reasons. It's hard to detect at the LHC for some reason. And so, you don't want to make a conclusion that's based on belief as to whether or not these theories are correct. All you can do is decide whether or not they warrant investigation, and I think they clearly do. There are very nice features of supersymmetry. For example, it contains a natural dark matter candidate. It has a particle that can explain dark matter. That means that it addresses one of those open questions that's missing from the standard model that I talked about. And therefore, it's worth investigating whether you can find evidence for it. But I don't ever really want to get into to discussing whether or not I believe a theory is true, because I do want to be driven by data and what the data say are there.
Okay, great. Thank you very much, Dr. William Barter. Some really incredible research. Thank you so much for being here, and it was a real honor hosting you.
Thanks. I hope the rest of your conference goes well.
Thank you very much. And on behalf of all Free Societies, we really thank you for taking your time out of your day and preparing your talk with us. So yes, thank you. And from everyone, I'm sure from everyone watching. If you have any more questions for Dr. Barter, okay. Okay. If you have any more questions for Dr. Barter, please post them on Slack. And we'll now take a 20-minute break for our final talk of the day with Professor Waugh from Oxford. Yes, we will see you then. Thank you.
Hello.